Welcome to Commit and Push, the podcast about how great software really gets built. I'm Damien Filiatrault, your host and the founder of Scalable Path. Each episode, I talk with founders, developers, and leaders about the decisions, trade-offs, and hard lessons behind successful digital products. Let's get into it. So I'm here today with Robin Hanson, who's associate professor at George Mason University. Robin, welcome to the podcast.
Great to talk to you again.
Yeah. So, I do want to get into some topics around the economics of the software industry, but maybe we could start off by you telling us a bit about your background and about how you got into the concept of rot and particularly software rot.
So I'm old, 65 now. And in 1984, I left graduate school where I had gotten a master's in physics and philosophy of science. And I went off to Silicon Valley to, on the side, do hypertext publishing and then I found a job doing AI. And so I spent 9 years doing basically AI-related software engineering at Lockheed and NASA. And that was from 84 to 93. And in 93, I started grad school in social science at Caltech. And that started my career to become an economist, which I have been for a long time, basically since then. So I transitioned from research software engineering, to becoming an economist. So in that sense, I have those as backgrounds. And I've learned a lot about many different aspects of social science and economics, but one of the things I've learned that I can bring to social science as a concept that most social scientists don't understand is issues in software engineering.
Right.
And one of the key issues in software engineering is that systems rot, i.e., the observation is that as you make a system larger with more parts and more interdependent, and then you try to change it over time to accommodate changing hardware, changing feature requests, changing human environment, etc. Typically, the changes create more interdependencies. And so over time, systems that have been modified that are large, they end up being harder to modify. Slowly over time, it gets harder to usefully modify them. And then typically, we just throw them away. We start over new systems from scratch. And that's just standard software engineering practice. And that's a warning about creating large systems and slowly modifying over time, is that this may be your fate, that you'll need to just throw it out entirely to start off with new ones. And I think that's just a neglected idea in social science. We have many ideas of systems and the issues they have, but we just don't typically think in terms of rot as one of the key features of social science systems. And I think it's promising to make the analogy in that direction. Now, I guess you could also try to think about the systems we have that don't seem to rot as much as we might expect. How could we make software systems more like those? But I guess that's a harder direction to go.
Well, we can get into that. Let's put a pin in that and talk about maybe some systems that you may know that don't rot as much. That could be interesting to talk about.
Sure.
But let me ask you a couple other things that came up in that. So one is, you mentioned that we often end up throwing things away, right? And I'm curious, do you a pattern that I've seen personally, and I've done personally and seen other people do, is like you get these large systems and instead of throwing the whole system away and building it from scratch, you kind of modify parts of it, or you refactor parts of it, and over time, and it's this is just a process that has to go on. I mean, is that part of?
Right. So that's the next subtler. There's the simplest story has you continue with it or you throw it away. The more complicated answer would be, say, there is this intermediate option of refactoring, and that it happens often, but not most of the time. But there are many systems for which we do this refactoring, and then the idea is that you'll replace some of the code and you'll be focused on sort of structure. That is, you'll be trying to restructure things so as to make it more modular, to make it better able to handle future changes. And so you won't just pick random parts of the code to change. You're picking the parts of the code that you think will most effectively allow a restructuring and allow more modularity, basically, more less dependence of parts. And that is often possible to do. But typically, this only delays. That is, there are very few systems which are just, indefinitely refactored and still around, say, after 40 or 50 years. That's just a very rare thing.
Well, yeah, that's quite a long time frame. I would agree. But I think it's, good that we're seeing things a little differently. It makes for interesting conversation. I've definitely seen projects that, and one of the things I think I like about software is that it's not like a, thing in the physical world, and where you're really constrained like with a home, for example. You've got the frame,
right,
the timber framing of the home, and you've got to live with that or tear it all down. Software is being code. It lends itself better to change, and you really can get a really clean slate if you take an area of the code and you clean it up and you write it in a more modern way. And I have seen projects where you just take a year or two and you say, okay, we're going to start with this part, and then we'll launch that, and with the rest of the system still there in the old way. And then the next quarter we'll do this other part and the other part, and eventually you refactor the whole thing, and it's like nice and shiny and new. And it can happen. I'm not saying it,
right.
It always does.
I mean, if you rewrote all the parts, in some sense, you did rewrite it all. You just did it in steps. But if you need to be saving at least some substantial part of the old code to call it refactoring.
Yeah, I guess when you say we throw it away, and it kind of seems like you really did write something new and then completely replace it. And I think I've seen that fail so many times, where you have a large system and people think, all right, let's just write a completely new modern version of this. And then they're working on that, and it's a huge project, so it takes a year or more. And while they're doing that, the requirements for the existing system change, and then they're updating the existing system in parallel, and then they're also having to update the system that hasn't launched yet. And that approach can be very fraught with problems, be very expensive, and sometimes completely fail because you're trying to do too much, and the business might just lose the appetite. And so I think I wanted to just draw that distinction between throwing something away and replacing it, which can be very difficult and costly, to just sort of, okay, let's take this 20% of it, modernize it, keep going. All right, let's do another 20%. Right. And we've tended to call that like the engulfment pattern, or like the I don't know if this is an official thing, right, but I much prefer that method.
Okay. So, but still, if we're replacing all the parts, but just one at a time instead of all at once, that may well be a wiser strategy for replacing a system. But you could also think of it as you did rewrite all of it. You just did it in steps.
Mm-hmm.
But if you saved, 30% of the old code or 70% of the old code, then I might say, okay, then you refactored, you changed parts of it, but you left lots of it still there.
Yeah. Okay. Well, we could. There's sort of like splitting hairs, and there's this sort of, I think a term that people have heard more in the world of software is technical debt. Do you see software rot as something different from technical debt? I mean, to me, it sort of seems like a different lens to look at a similar problem.
It's the same causal process you're pointing to, but you're thinking in terms of different ways to deal with it. So technical debt, you're thinking, well, if we wanted to sort of keep the system at a similar level of maintenance or, ability to add features, etc., we would need to be paying a certain amount of effort to the system. And if we fail to do that, we're later on, if we want to do those things, we'll have to do more effort later to compensate for the lack of effort now. And that's the debt. So the debt is, not paying things now, and as a result, having to pay more later.
Right.
But it's pointing to the idea that there's work to keep something able to be maintained and able to be, changing its context and integrating new tools. But the technical debt is, I guess, framing is missing a bit, that you might not pay these costs now because if you're going to maintain it, you'd have to pay them later, but you might decide not to maintain it later. You might decide to just drop it.
Yeah.
In which case it makes sense not to pay those costs now because why bother if you're just going to drop the whole thing?
Yeah. I mean, one thing that I never really thought of when I first learned about technical debt, you have some people that are like, no, we always need to be paying it down. Like that seems to be some people think that's the best strategy. But if you're, a startup and you've got to go to market to beat your competition, sometimes just, getting something up quick and dirty and getting a bunch of users. And you don't have this system that's perfect or necessarily maintainable, but you got twice as many users as your competitor, and that was worth it. And then you can, pay that debt down later. But
maybe there was only a 20% chance this business would actually work. And in those 80% of chances, you don't have to pay the debt later because the whole thing is just rejected. So, you're gambling on, will this even get traction? And then it makes sense. Yeah, why pay a debt on the, commitment to that you'll need it later, but you might not need this later because it might not get any traction. You might just not get customers and the whole thing stops.
Right. So this concept of rot, have you seen it in other areas of economics that you've, and you mentioned before, like other systems that don't rot like software, but is this like a concept that you've studied in other industries or sectors or?
Well, so I am an intellectual who mainly looks for what I see as neglected important questions. So I would say I've noticed that rot is neglected outside of software. And that's why I think it's interesting, because I think, well, maybe there's a place here I can say something that other people haven't said that's interesting and worth saying. So I have not seen many other people talk about rot outside of software. And so that's why it's interesting to sort of compare these things and try to bring these literatures to see each other. Now, we do have other kinds of systems, as you mentioned, non-software systems like houses. And we're all familiar that these other systems rot, right? Organisms rot, food rots, buildings rot, cars rot. But our go-to explanation for that rot is usually just decay of parts. Maybe there's termites in the house, or, you didn't paint it enough and now there's rot, mold or whatever. So in other systems, we just see the parts decaying at such a rapid rate, and that it just seems like a pretty good explanation for why the whole thing fails. And that's why software is interesting, because with software, the parts don't rot. Each bit can just be absolutely saved. Nevertheless, the whole thing rots. So now you realize, there's another kind of rot that software shows you. And that's happening in all the other systems too, but it just may be less important because of the other kinds of rot that are happening. But even if you could fix all those other kind of rot, there would be this kind of rot that we see in software. And that would be a limit on how long a house could last, or a car could last, or other sorts of systems could last without paying these costs. And that's, I think, helping you see what other processes are happening in other systems. And so we have, as a society, many large systems that last a really long time that we rely on. And so the phenomenon of rot makes you wonder, should we be worried about rot in these other large systems? So think about language as a system. Languages have many parts, components that work together over time, and languages change over time. Could languages rot? Think of legal systems or regulatory systems. Lots of rules get collected, precedent, add on top of each other. Could legal systems and regulatory systems rot? And then we might even think of sort of a whole industry, I don't know, say the movie industry or something, where you have a structure to it. Like there's all these different parts. You have the studios, you have, the writers, etc. And it accumulates a structure, and that structure lasts for a long time. You might think, could those structures rot? Could whole industry supporting structures rot? And certainly in many areas of software, not just individual software systems, you have whole systems of software, right? The whole internet protocol, say, has all these different levels and all these different interlocking parts, and you think, could that system rot? And so the idea of rot is this pregnant warning about other systems you're familiar with. So that's why you want to ask, okay, what do we know about software rot? Like what distinguishes when it happens more or less, which things don't seem to subject to it. Those are important clues to where we should worry about the problem more. So for example, if you think about, say, matrix inversion software or matrix multiplication or other sorts of matrix, tools, we have such a stable interface. Definition of what a matrix is, definition of what a matrix inversion is, even that you can make software that just does matrix inversion and it hardly rots at all. Especially if it can call some abstract concept of multiplier or add or something, that you can replace the representation of a number and how you do a multiply, etc. But the overall higher level structure can just last. And basically it's a combination of, it's just not very complicated. And
I feel like
interface is very stable.
We're going to lose some of our audience talking about matrix inversions, but you're talking about just mathematical software,
right, with very stable mathematical concepts that have been around for a very long time, and that therefore they don't need much change. So those are things that can last. And you might say, look, it actually doesn't seem like languages are rotting.
Well, I don't know if you look at the way younger people are texting these days. I don't know,
society could rot in many ways, but it doesn't look like it's because of the structure of the language they're using. That's the main problem.
Yeah, I guess I'm just.
That's not like grammar is failing them or anything, or their vocabulary is failing them. I mean, those seem to be working just fine. If they have problems, it's at other levels.
Yeah, that's quite an abstract problem that I haven't. I don't know if I'm able to wrap my head around how a language can rot. Are there examples of that happening?
I mean, what I know is the larger a community that uses a language for the longer, the larger the vocabulary tends to be, more conceptual distinctions they can make, but that mostly seems to be good, that they have more distinctions to make. So again, what I know of languages, they don't seem to rot. And so maybe that's an encouraging feature. Language is simple enough and maybe robust enough in the way it's set up. Another standard example, as you probably know, is that many organizations need to be reorganized, right? And if they had maintained their old organization structure since the very beginning, they would just be doing a lot worse. Mm-hmm. And so you might say organization structures rot and they need to be refactored regularly. But fortunately, that seems like we just can refactor organizations, but organizations do seem to rot. That is, when we look at sort of profitability of companies and their growth rates, it does seem like all else equal, older ones do worse. There's just a tendency for old companies to find it hard to compete with new young ones because something has accumulated in them that's hard to change. Mm-hmm. So companies rot.
Yeah.
But we have this process of replacing them so that overall society isn't suffering, because most organizations just don't last that long. Half the Fortune 500, the S&P 500 wasn't on the list 20 years ago. So they're just not staying around that long. And so the corporate world rot is less of a problem because we're just replacing them so consistently.
Mm-hmm. So a quick pause here. I wanted to tell you a bit about why I started my software staffing company, Scalable Path. Back in 2008, I was working on a client project with some developers in Argentina, and I saw how amazing it was working with people in my time zone who were just as available as people in my office. So in 2010, I started Scalable Path to help companies take advantage of this underutilized talent pool. And since then, we've built a platform of over 40,000 developers, and we've placed over 600 of them with over 300 clients. So if you're looking to hire top-notch dev talent at a fraction of the cost of hiring locally, visit scalablepath.com/commit-push. And as a listener of the podcast, you can get 20% off your first month. I'd love for you to give us a try. Yeah, I was reading the Wikipedia article on software rot, and they listed a bunch of causes. There was environment change, which is when the problem that the software was meant to solve actually changes, and then the software becomes rotted. Something called onceability, a lot of unused code, rarely used code, online connectivity, rotting because it's being changed too much, rotting because it's not being used or rarely used. There's a lot of different reasons they list that sometimes some of these things are things we just sort of take for granted. We go, oh yeah, well that, you don't think of it as rot. You just, as a software developer, you're like, oh, the server's not connected. Let me bring that back online. Or yeah, we're changing a lot of things. It got a lot more complicated and we need to refactor this. Yeah, interesting concept, software rot. I mean, are there any recommendations you have for software developers on how to build systems that are less prone to rot or how to deal with it?
So I haven't been practicing software engineer for a long time. So I feel like I'm going to defer to your expertise vastly more on that than mine. I'm mainly feeling like this is something the rest of non-software engineering should learn from you guys about. Mm-hmm. And I'm less knowing what I could tell you about how to deal with your problem. But basically the fact that most of the world doesn't even notice that other systems rot might be a warning that maybe you might not notice it as often either. You might.
Well, I'd come back and say, that if you want your system to stay functioning for a long period of time, you're going to have to refactor parts of it to keep it fresh, but also recognize, as we said in our little discussion of technical debt, that sometimes it's not the right decision. Sometimes the best decision is just to keep costs down, keep running your business, and know that you're accumulating this debt or rot, and do it at the right time when it makes sense. So
here's a more software engineering question, which is, when you have code generating software, is it more or less susceptible to rot? I think if we look at, say, code generated by, say, compilers or something, you could imagine, say, a compiler that took the previous compilation and modified it to compile a modified version, or what people typically do is they go back to the new code and they just recompile everything. And that's a sort of starting over from scratch, basically. So the compiler doesn't believe that if you make a small change to a piece of compiled code, that it will be able to make local modifications to its compiled code in order to make a new version of the compiled code. Our practice believes, no, you just start over from scratch, right? And so it does. So we have other sort of higher level writing software we've had for decades. And that seems to be a similar practice, that we just go back and we start over from scratch. Even say, if you look at AI practice, they have a data set and they train an AI, and now they get like an addition to the data set, but they tend to go back and start a new AI all the way from scratch on the whole data set, right? So that's showing they expect it to be hard to do the modification thing. It's easier just to redo from scratch.
Yeah, I mean, it brings up kind of an idea of what people are doing now with having AI write code for them. Would it be, if you can generate, obviously compiling from a higher level language into a lower level language is a very low cost operation. So that's why it's efficient to just say, oh, let's just redo the whole thing. It only takes a computer X number of minutes, right? If it took you 6 months to have developers build your system, you're less likely to say, all right, let's just rebuild the whole thing, right? It took you $100,000 to do it. So you're going to say, oh no, let's modify this thing. But if, we're entering a new world where you just prompted an AI to write this complicated thing and it didn't cost much money, then maybe we could be getting into the realm of, maybe you just prompt it again. Maybe you have some spec document that you change that the AI is reading, and then you just reprompt it and it just builds the whole thing again. And it might even use a different language
Okay, but it's not so much about the absolute cost as the relative cost here. Even if it's cheap to recompile things, if it was even cheaper to incrementally recompile, then that's what we'd be doing.
Right. They're relative. Yeah.
So the point is, it's actually hard to incrementally recompile.
Mm-hmm.
And therefore, that's why we do the just recompile everything.
Yeah. And it is, I think
that's something to notice. Like, it is hard to incrementally change things for software, for automated code.
Yeah, it is. And all right. Well, so maybe this discussion of AI is kind of a good pivot here to the next part I wanted to get into with you. I think one of the biggest questions on software developers' minds these days is, how good is AI getting at coding, and are we going to be replaced? Is there not going to be as much work for humans because there's going to be this very affordable AI that can code? And so on one hand, there's this fear of having less work and making less income as software developers. But you've also, as an economics professor, looked at the theory of like, okay, well, compensation or wages is tied to your productivity level, right? And I want to get into like the economics behind that, but you could also look at this as a developer and say, okay, well, if I'm orchestrating these AI agents and, that's making me, if someone employs me and I'm using these tools, I'm going to be, so much more productive. Maybe there's actually more money to be made as a software developer because you have these tools to be more productive. So can you get into the economics sort of behind that?
Right. So imagine you're a violinist in an orchestra, and we are threatening to automate violinists. Now, if we make violinists much cheaper, that really won't expand the number of orchestras that much. So therefore, the demand for people like you is going to go way down. Now, maybe you can get one of these rare jobs as the violinist automator or something, but there's just going to be a lot fewer demands for those things because the demand for violins is just not going to go up much, even if we automate it. So basically,
because there's still going to be the same number of there's going to be the same number of orchestras,
and then roughly the same number of violin slots.
Right.
And now they're just going to be done by machines instead, and so the orchestras will get cheaper violins, but there won't be that much more demand for violins. So you're the violinist. You're just going to lose. You're going to have to find something else to do. But software is a very different industry.
Well, can we stay on that analogy? Like,
sure.
Maybe you could say, I think where you could take that is like, if they were going to automate every instrument in the orchestra, then orchestras would be, then the cost of the whole orchestra would go down. And then
now the question would be, how many more orchestras would people hire if orchestras were a lot cheaper?
Right.
Would you do them for your birthday parties? Would you do them for, work parties? Like how often would you hire an orchestra if it could be cheaper? And so that's about the elasticity of demand for the whole industry here, which would be more elastic than for each violinist, but it still might be modest. Maybe there's just not that much more demand for orchestras. But software is an industry with a very elastic demand. That is, there's just lots of businesses in the world that look at all sorts of parts of their business process and say, gee, should we try to automate this? And they go, gee, software is really expensive. Not yet. Let's wait till it gets cheaper. So the world is really eager for software. All over the place. And the main limitation is just expensive to write software. So now, if you could automate software and make software cheaper, there's just a huge world of demand for that.
Yeah.
Lots of firms will just do a lot more kinds of software when it's cheaper to do software.
Mm-hmm.
So now, if you get automated assistance to your software engineering and it makes you productive, now the overall productivity is also going to go up because the machine is like, the machine makes you 10 times as productive, right? Well, now we do have to pay for the machine. So the product doesn't get 10 times cheaper. Maybe it gets 5 times cheaper, but it gets a lot cheaper when you are now 10 times as productive per person. But now your wages should just go way up. And so the straightforward prediction of making software engineering more productive, because software engineering is this thing with a huge elastic demand, is that the size of the software industry should just go much larger, much more revenue goes into it, and then software engineers get paid a lot more because the whole thing doesn't happen without them. That's the prediction for at least the near term of, much more productive software engineers because they have these tools. Now, yes, eventually maybe they don't even need you. The software tools do everything, but we're not close to that.
Yeah.
So
I think that from what I've been reading and hearing, that we're not really there at all. Like, you still need all levels of software developers, but we may not be far. We may be 3, 5, 7 years out from AI software agents being able to play the role of a more junior or entry level software developer. And so I kind of see that playing into this, elastic demand industry growing, wages going up. It may be disproportionately benefiting and hurting different levels of seniority in software developers, in the next decade. So like, if you're a senior person, you may benefit from this because you have the expertise to do all this orchestration of these tools. And whereas if you were someone right out of college, looking to gain experience by doing simpler tasks with a company, you might find less opportunity because there's AI agents that can do that sort of work. Thoughts on that?
You'll need to learn to do the valued tasks. But, in general, if there's going to be this huge increase in the demand for the valued tasks, then people will be willing to pay to be trained.
Yeah. So
pay
computers
for training to produce those people who can fit those roles.
Yeah. Okay. All right. So I mean, it sounds to me that you're, as an economics professor, saying the sky isn't falling. It's just going to change. Things are going to change, but overall, it may be a good thing for the software development industry.
I mean, so we have to distinguish sort of short-term and long-term changes in AI. That's always been the issue. So we've been talking about relatively short-term changes.
Okay.
Now, if you want to think about the world where AI does everything better than all humans, now we've got a different world to describe and think about. But that's not what we're thinking of in the near term here. We're just thinking about productivity changing, humans doing different tasks and machines doing other tasks.
Yeah. I mean, I'm tempted to go into that other subject with you. I mean, do you have any high-level thoughts on have you explored?
I've had many high-level thoughts on that, but it would distract us from other topics.
Okay, I won't go there. Okay. As you may know, I run a vetted talent platform called Scalable Path, and I'm offering a 20% discount to listeners of the podcast. So if you're interested in scaling your dev team faster and smarter, visit scalablepath.com/commit-push. You mentioned when we spoke earlier that you think the population, the world population, is going to start declining at a certain point in the future, and that will lead to economic decline. How far out is that, and how do you see that? Do you think that will affect all industries equally, or do you think that might affect the software development industry in a particular way?
Software will be affected in particular ways, yes. So the first thing to say is we roughly guess world population will peak in like 30 years from now, which is well before the UN prediction, but UN predictions have just been way wrong for a while. At that peak, there'll be parts of the world that are rising in population and parts that are falling. The parts that are rising are mainly Africa and the Middle East, very poor places. And they may not be able to pick up the innovation, task that's passed off by the then declining population of, say, Europe and China and the United States, et cetera. And so it might be that growth rates peak before population does. That is, we might start to decline the rate of innovation in the world before population even peaks, so maybe 20 or 25 years. And then what we'll have is that as population falls, the size of the world economy will fall and the innovation rate will fall even faster.
I guess maybe we should define innovation rate and a little, because I think you threw that in there kind of unexpectedly.
So our standard idea is that the world can produce stuff because it has labor, skilled labor, it has machines, capital, real estate, and it has ideas. And innovation is the accumulation of more ideas, more ways of doing things, more insight. And our standard model of innovation, the accumulation of ideas, is that we just add more ideas to our pile of ideas in proportion to our economic activity. So the more stuff we do, the more ideas we generate. So when the world economy peaks, then that's when innovation rates would peak, if not for this correction factor I was just describing. And then as the world economy declines, because population is declining, innovation rates will decline. That is, we just won't be doing as much, so we won't be adding as many innovations to the pool of innovations we have so far. And once we are, say, down a factor of 10 or even more below the peak, then innovations rates will be down by more than a factor of 10 or more from the peak. So we will just perceive a much slower growing economy. That is, there'll just be fewer innovations that show up. And so that's a first thing to realize. In a declining economy, innovation will just slow down, apparently, to a halt. It'll just slow. And as you know, the computer industry has very much depended on expectations of innovations, improving hardware and software for a long time. So that's a different image of the software engineer industry. It will be an industry without those innovation changes, first of all. So then you won't have better new hardware, you won't have better new software. You will be using the tools you have and maintaining the tools at the level you have. But then secondly, software is an industry dominated by fixed costs. That is, there's the cost to make software and maintain it, and there's the cost of servicing each new customer. And those variable costs of servicing each new customer are relatively low. It's mostly the fixed cost. So this fixed cost dominated industry is very sensitive to the scale of the economy. If the economy falls by a factor of 2 in total, we can only have half as much software support. We either have to grow the size of the software industry compared to the economy, or we just have to drop half of our software in terms of being able to create it and maintain it. So we now have this huge infrastructure of all this software built on all this other software that we continue to add to and build on top of because, growth is growing so fast and computers are getting cheaper so fast and it's easier to store all the old software. But as the economy declines, there'll be all these software that could afford itself with the old number of customers, but now as the number of customers decline, they can't maintain it and they just have to drop it. But now all the things that are built on top of that would also fall. So those falling house of cards of software, basically the things that last are the kinds of software that are not built on very many other things that are expensive, at least, so that they can maintain themselves. That's what I call software biting the world. People have talked about software eating the world, but now software bites the world. Basically, software says, look, we have all this fixed cost to pay for. Somebody's got to pay for it. Fewer customers, you got to pay more. And that'll be the key trade-off as the world economy declines, is what kind of infrastructure will people be willing and able to continue to pay for? And one last thing to notice is computer hardware is actually intrinsically pretty durable. We don't tend to make it very durable because it's been improving so fast. But when innovation falls away, then it'll be worth the trouble of making computer hardware durable. And then you'll make a generation of durable hardware, and then the world will just shut down all these factories because the old durable hardware will be plenty of hardware for the future as the world economy declines. So you imagine stable languages and stable, levels of abstraction in terms of the efficiency of the hardware, but then people are just using older and older hardware because they're not making any new. And then various tools fall away because nobody's able to pay for their maintenance to keep them going. So that's the future world of software when population declines.
Well, there's your more dire outlook as opposed to your positive outlook on the elastic software industry. I mean, clearly you've thought about this a lot, and I don't expect you to educate me on, core economic theory here, but the part of this that's a little bit hard to swallow for me is sort of generalizing human behavior, in terms of population. Is that just a widely accepted view that, that you can extrapolate from population size? I can swallow it a little more on the economic growth. Of course, that kind of makes sense, but sort of saying people will stop, even if you had a lower population, if there was still this sort of core subset of the population that was still highly innovative. Is that possible? Is it that we would still maintain innovation if there were people, like,
right,
even if it was a smaller number, who were driven to improve things and solve problems?
So Silicon Valley is a thing. It's been a thing for half a century at least. And a lot of the world has said, look, per person, Silicon Valley is a lot more innovative than the rest of the world. So they don't believe this per person thing. They say, look, some places can just do a lot better than other places. Why can't we do more of that elsewhere, right? That would be the pushback, is saying your simple model of just proportional to the size of the economy set doesn't take into account the fact that we see all these places in the world that seem much more innovative than other places. And you think, why can't we copy that? And as you probably know, over the last half century, a lot of other places in the world have said, we want to be the next Silicon Valley. And they have put money into and tried consciously to make themselves like Silicon Valley so that they could be innovative like Silicon Valley and make all the money that Silicon Valley does, right? And they have consistently failed. That is, even if there's variance in the world, it doesn't mean you know how to copy it. And so our simple model of this average world is based on the idea that you don't know how to take the better parts and make the other parts like that. People keep trying, they have strong incentives to do so, and they are largely failing.
It seems like that's a valid point, right? That's a valid observation, right? And that people have tried to duplicate Silicon Valley, but does that unsuccessfully, but does that actually support the idea that a lower population will have lower innovation?
Well, I mean, the key parameter here would be innovation per capita, right?
Mm-hmm.
Or innovation per economic activity unit.
Mm-hmm.
So then we look around the world, we say, well, we do see large variation in innovation per person or innovation per economic activity. So, for example, we see larger cities, more central cities are more innovative than rural areas. We see, other correlates of who's more innovative. The United States seems to be more innovative and Europe is falling behind, but China may be catching up. But when we look at, say, Africa or the Middle East, they just don't seem to be picking up the levels of innovation. Even if they're getting richer, they're just not getting that innovative. And so it just seems to be really hard to copy the innovation. Mm-hmm. And in some sense, our world is innovative on a certain average level, but much of the innovation in the world is concentrated in a few rare places. And that means, yes, in principle, if you could copy those rare places and make everything else like them, we could have a lot more innovation. Oh. But again, people just keep trying and failing at that.
Yeah.
And in fact, places that were more innovative have gotten less innovative, say Europe. And so there seem to be forces to degrade innovation, maybe analogous to rot. There are ways in which society once had an innovative place and they screw it up somehow.
Yeah. Well, I hope that we can maintain, because I do think population going down would be a good thing for our planet, but I hope we can maintain our innovation despite that, and we will see. Well, I really appreciate you coming on the podcast to give a different perspective. This is, a much more theoretical perspective than we normally get, but I think it's a nice, fresh breath of fresh air. So thank you for that. Is there anything you want to share with the audience, or, like something you're working on, or where they can get in touch with you?
Well, I'll just a quick sentence. My big thing for the last 2 years is this idea of cultural drift, the idea that the cultural evolution process, that's humanity's superpower, parameters have gone wrong in the last few centuries, and now we are drifting into maladaptation. And that's a concern I have about our overall culture and humanity's future. That's not, extinction isn't the problem, but our mainline collective, world civilization could collapse and be replaced by other now very small subgroups who are, deviant in many ways. But that's, if that topic's interesting, then, you can look me up. But otherwise, thank you for listening.
All right. Well, Robin, it's been a pleasure. Thanks for your insights, and really appreciate your time.
All right. Take care.
Well, that's a wrap on this episode of Commit and Push. If you found it valuable, subscribe on Apple Podcasts, Spotify, or YouTube. And if you're building a team, check out scalablepath.com to find top developers. Until next time, keep building, keep pushing.